record. So what can we do with this? Just to go back to our original plan. Over here we said we want to create a stack as an object. This is the data type. User-defined data type. We define that data type. We want to be able to reset it. We want to be able to push values on it. In this case, we're moving towards ability to push multiple values, like this, and then to be able to restore those values also by using multiple calls to pop, and we can use the same variable, or we can use multiple variables, or whatever, or we can even pop values and instantly throw them away, because we don't, we're not obligated to retain values returned by functions. We can just ignore return values. So these are all possibilities of using the stack. But this time, every time we push, the stack's supposed to use new element of storage right here. This is called an array, and this is the syntax to create an array. And guess what? This array of 100 integers is created immediately as soon as we say we want to have a stack. Another quick modification that I'd like to attempt here is that instead of saying m value, which is no longer something I want to be using, instead I say this will be our stack pointer. Don't mix it with C++ pointer. This is just a number. Shut this off. This is unnecessary, but it's good to see because we know it's saved properly. So this new helper variable is going to tell us which part of the storage we're currently looking at. For example, if I go back to the drawing board and move it, actually I can probably move CPP to the previous step here. So m value is gone. So let's start with reset, because reset is like, first of all, I probably want to put my stack pointer equal to 0, right? I mean, that's what I want in my reset, right? Next, when I store the element by push, I get my 555. But this is what I'm going to do. I'm going to say storage, right? Storage. And the location of storage is, of course, the stack pointer, right? Stack pointer. And store value in this location. This is the standard syntax how you access array elements. You have to specify the name of the array. This is the name of the array, right? And this is the index or subscript to which place in that array you want to go. This is supposed to be ranging from 0 to the size of an array minus 1. And as promised, as Eric asked already, we can say, we can do it directly here. We can say static const int stack size equals 100, and then use stack size constant in place of this. I will talk about this part next Thursday, next week. We're going to talk about statics, static member functions, static variables. But in order to be able to create constant inside the class, it has to be static in order to be initialized, in order to, to be possible to initialize it using the initializer. More on this later. But this is how you declare a variable, which is constant inside your class. And so now we can use stack size. Even more so, I think it would be good to say initial stack size. Or I don't know, in the future we can make this we can make it a variable when we adjust the implementation of our stack. But for now, just say initial stack size, and that's kind of self-explanatory. So, naturally, we require the user of our stack to call reset. Remember, we said unless you call reset, nothing's gonna work, because this will be garbage value. Garbage value will be used to access memory location. Most likely this is going to crash miserably because of the memory access violation. So this is how now we can access our storage based on the stack pointer. And again, nothing to do with the pointer, but simply a logical name for a subscript that we continuously use to point to places in our storage. And then, of course, the pop, which is supposed to return an integer, supposed to just return this, I think, right? Just return what was stored. Nothing changed that much. We're still, we're still not there yet. We created an array of 100 integers. We used constant variable named initial stack size. We know it's 100. As soon as we do this in our code, as soon as we say in stack, those 100 integers are going to be established in memory, part of our object. In fact, another integer, MSP, is also instantiated, and all of them contain garbage. But then reset takes reset takes place as the user promises to make this call, and at this point stack pointer set to 0. That's good news. So now the 0 can be used to access the initial element in this array. It is now part of push and pop. But as soon as we store the element, we probably should do this, right? Say, okay, if the next time you push again, well, guess what? We already got ourselves adjusted, and now we're ready to accept another element. Meaning what? So that we have, remember how I was drawing this free store thing. So now let me try this. So I have this M storage allocated as this int, and so forth, right? Int. They have index assignments 0, 1, then 2, right, and then so forth. This is 99. If I overstep boundaries in any way, I'm going to be punished, right? It's going to be memory access violation. So initially, MSP is kind of like pointing to here, right? That's where it's pointing to, right? So we purposely set it to 0. So whenever I say M storage with index MSP, I am going to this location, and that's my integer. I'm going to push there or retrieve the information. But as soon as I say plus plus, SP kind of becomes 1, and so therefore I move on to another location in the storage. Pretty good. Then all of this is done in anticipation that there will be another push. But what if there is no another push? Instead, someone wants to pop the element. In that case, we instantly have to say, oh no. First, let's just instantly step back, right? Because we intentionally step forward anticipating there will be another push, but it didn't happen, so the pop occurs, so we have to reduce MSP instantly. Because, for example, if I did this, right, if I first push was and we stored 555, right, then stack pointer moved on, logically moved on. We just incremented the integer value. It was 0 to begin with, it became 1. right? So now this is where we are. MSP is 1. We know that this element of storage contains 555. If now pop occurs, then we instantly go back to 0, right? We go back to 0 in MSP, and we return this. We return storage with index 0. So we will return 555. Agree? That's it. The only thing to do is to say how to also support and implement, hopefully, some perhaps boundary checks, making sure that, for example, there was this requirement, and look, this is a typical case of you programming here, is that someone says Boolean is empty, right? Is empty. Is stack empty? Has anyone ever pushed anything on it? So we do this, right? We want to add this to our interface, and then we also want to, it really doesn't matter in what order you do this, but you want, I'm just pasting it here, right? In stack is empty, get rid of this semicolon, and say, well, if apparently I can only rely on MSP to know everything about my stack. So I can just say if MSP, spell it right, if MSP equals equals 0, I guess, right? It means that they never pushed anything, or they popped everything already, because this happens only after reset. As soon as anything is pushed, MSP moves on, because that's part of push. We instantly say, no matter what happens, MSP moves on, is incremented, right? So if MSP happens to be 0, which of course a lot of programmers will write like this, if not MSP, because in C++ anything that's not 0 is true, anything that is 0 is false. So whichever way you prefer, right? So I'll just keep this on. So we'll say if stack pointer is 0, then yes, return true, because yes, the stack is empty, indeed. And otherwise, I don't even need to have an else here. Just simply say return false. Right? Just in any other case, the stack is not empty. Okay, so that's another demonstration for check whether it's empty. And by the way, all stacks are designed with this responsibility of the user in mind, that they're not supposed to attempt to pop from an empty stack. As well as if stack does have limitation in terms of this, right? We have only 100 places to store. As soon as they want to push 100 first element on the stack, we're supposed to do something about it. Maybe we could print a warning message or something. We'll see. This is going to be covered in our next class.